Okay, welcome back, everybody. So, I wanted to say one more thing uh, about harmonic functions before moving on. So I wanted to illustrate a technique for finding a harmonic conjugate of some given harmonic function. Uh, and this is a technique that is very similar to things that you've seen before in various courses. So in both Calc 3 and differential equations, you've seen very similar types of things being done. And so let's say that I have the following example. So if I have a function of two real variables given by y cubed minus 3 x squared y. Okay, then if we check really quickly, I won't check, but I'll just say that if I check what the Laplacian of u is, it's actually equal to 0. And so this is true in the entire xy plane. So true in the entire xy plane. Okay. All right. And what we can do to find, so if I want to find harmonic conjugate V, what I make use of is the Cauchy-Riemann equations, and I attempt to solve them in kind of a step-by-step way. Okay, and so Cauchy-Riemann equations, of course, are following. So this is u sub x is equal to so u sub x is equal to v sub y, and u sub y is equal to minus v sub x. Okay, and so for instance, like all I need to do is find v satisfying the Cauchy-Riemann equations here, and I have found the harmonic conjugate that I'm looking for. So I take the x partial of u. So the x partial of u, for the y term, that's 0. The x partial of the second term is minus 2 times 3xy, so this is minus 6xy. So this first equation means that minus 6xy, that's u sub x, is equal to v sub y. Okay, so any v that would end up being the harmonic conjugate of u would have to satisfy this. Okay. And so the idea here is I can look at these. These are first order. This is a first order system of PDEs here. And I want to actually integrate with respect to y here, right? So I want to integrate with respect to y to find what my v of xy would have to be, what form it would have to take. So if I integrate with respect to y, both sides of this, so this is an explicit PDE, right? So all the derivatives are on one side. Or I should say, the single derivative is on one side, so I just need to integrate here. So v of x y is equal to, so the integral of minus 6xy with respect to y is, of course, minus 3xy squared, plus some constant of integration with respect to y. But a constant of integration with respect to y, or rather the most general way of writing that constant, would be as a function of x. So maybe we'll call it h of x. Okay, and so the general form of a v of xy satisfying this equation looks like this. This is minus 3 xy squared plus some function of x. You can just check, of course, that if you take the y partial of this thing, you get exactly that. But of course, this v doesn't just have to satisfy the first equation, it also has to satisfy the second one. So now that we've found this form that v takes, we apply the second Cauchy-Riemann equation. Okay, and I take the x partial of this thing. So what is the x partial of this thing? Well, the x partial is, so on the right hand side I'm going to, so the x partial is going to be minus 3 y squared plus the x partial of a function h of x is actually just the full x derivative, right, of that thing. So that is the x partial of e. So minus the x partial of e is equal to the y partial of u, which I can just compute directly from here. So this is 3y squared minus 3x squared. Right? As the y partial of minus 3x squared y is just minus 3x squared. Okay, and so rewriting this, this is 3y squared minus 3x squared is equal to 3y squared minus h prime of x. And so the 3y squareds cancel, and at this step, if this process is going to work, this has to work out this way. And so h prime of x is equal to 3x squared. Okay. So that when I integrate with respect to x, I find that little h of x is x cubed plus some constant of integration, right? And any function of this form will work. So going back, this tells me the form that this harmonic conjugate would have to take. And so v of xy, which is minus 3xy squared plus x cubed plus a constant, this is the harmonic conjugate of u. So, okay, of this u of xy specified. And so we could actually form an analytic function here on the xy plane that is given by, so f is equal to u plus iv, then is analytic on the xy plane. Okay, for instance. Okay. All right. So this is this can come in handy, and as I said, you have probably seen a form of this one way or another. Okay. So I wanted to mention a couple of neat properties of analytic functions that we're not necessarily going to use immediately, but can be helpful to us. So, well, I should say some of them we're going to use immediately in the sense that I'm going to use them to actually smooth over some of the talk that we're going to be doing about what are called elementary functions. Okay, and so the first property I want to talk about is the unique determination of analytic functions. And after I state this, so there's an initial lemma, and it won't entirely be clear why the lemma is important. The lemma is going to let us prove an important theorem, though. And this theorem is important because of a process that we're going to make use of to define nicely some of these functions that we want to talk about soon. Okay, and so your textbook calls this a lemma. And so suppose that firstly a function f is analytic throughout a domain D. Remember, domain means open, non-empty, and connected. So secondly, f of z is equal to 0 at each point z of a domain or line segment contained in D. Okay, so I have a function. It's analytic throughout some domain D. And it's equal to 0 at each point of some subdomain or at each point of some line segment. So here's D. D is a domain, so maybe I shouldn't have drawn the boundary in here, so you can think about the boundaries not being included. Let me put it in a different color. Right. Yeah. There. Okay, so here's my domain D. and then there's some subdomain, maybe. Right, and then I'll call it d prime. So say f, I have a function f analytic on this domain. Maybe it's entirely 0 on this other domain, d prime, it's a subdomain, or on some line segment that's in the domain. Okay. All right, then the conclusion of this lemma is that f of z is identically 0 in D. So it is actually identical to the constant function 0 on the entire domain. So this is identically 0 on D. Okay. Now, what does this have to do with unique determination? So I'll show you exactly what it has to do with unique determination in general, but this is just a specific example of unique determination in the sense that what this lemma is really saying is that if we have an analytic function in some domain, well, there's an easy function that is seen to be analytic, which is just a constant function, right? So consider the constant function 0. Right? So on this domain D, it's just the function that's identically 0. Well, this function f that I started with actually shares values of that other analytic function, the constant function 0, on either subdomain or line segment contained in my domain D. And if it does, then it turns out that it actually has to be 0. Okay, so if it shares enough of the values, enough here being a subdomain's worth or a line segment's worth, then it actually has to be the constant 0 function. So this is an example of unique determination, that I have two analytic functions, but I know that they share the same values on some subdomain. It turns out they have to be equal. Now, one of those functions, of course, is just the constant 0 function here. Okay, but this is the important case, it turns out. Okay, so this is the important case. Now, to see that this is actually the important case, I will go through the reasoning here that illustrates that that's exactly what's going on. I'm not going to prove this lemma, so the proof of this lemma is on page, I think it's 83 and 84 of the textbook. Let me check. Yeah, 83 and 84. Bottom of page 83, top of page 84 proves this lemma. So I won't prove it. It doesn't take too long. It's like 2 paragraphs. But this is actually the important thing for what I really want to say. So I want to use this lemma to talk about the general unique determination of analytic functions. So now, suppose f and g are analytic in my domain D, okay, and f of z is equal to g of z, okay, at each z in some domain or line segment contained in D. Okay. Well, then, this is a standard trick in analysis. There's many standard tricks in analysis. Here's one such trick. I can define the function h of z to be, say, f of z minus g of z, right? So it's a difference of two analytic functions f and g. Well, then h is analytic. So h is analytic on D, and since f of z is equal to g of z at each z in some domain or line segment contained in D, then h is equal to 0 on some domain or line segment contained in D. But then by the lemma, implies that h of z is identically 0 because it is analytic and it's 0 at each point in some subdomain or line segment, okay, contained in D. So it's identically equal to 0. But if h is identically equal to 0, then f is identically equal to g. So this is what we mean by unique determination of analytic functions on a domain. It's that whenever you have two analytic functions and they share the same values on some subdomain or a line segment contained in your domain, then actually they're equal. They agree everywhere else, too, on that domain. Okay? So we actually just showed that this has to be the case, all right? And I'm going to restate this as a theorem, but we actually proved that theorem that I'm about to restate from this. So the lemma is really all you need for that. So that's why it's important to have this lemma. So really, what we proved is the following theorem, which is that a function that is analytic in a domain D is uniquely determined over D by its values in a domain or along a line segment. So by its values in a domain or along a line segment contained in D. When we say uniquely determined over D, that's exactly the statement that if you have any other function that shares the same values as that original function on a subdomain or line segment, then actually it has to be equal to that original function. Okay? All right. So this is important to us. Now, why is this important? So why is this, maybe I should say, why is this nice? Okay. Well, the main answer is this helps us with extending the domain of definition of an analytic function. Now, this process of extending the domain of definition of an analytic function has a more concise name. Okay, so this is known as analytic continuation. Okay. So what is analytic continuation? Okay, how does it work? So the idea is the following. So analytic continuation works like this. So the idea is that if I have let's say that I have two domains, say D1 and D2. Okay, so I have domain D1 and D2. Maybe here. Okay, I'm going to draw a different. I need more room anyway. So let me draw a picture of how this works. So the idea is that I have some domain D1 and I have another domain, say D2. Okay. Then this overlap right? The sets they have in common is, of course, their intersection, d sub 1 intersected with d sub 2. Okay. All right. The idea is that, let's say that this intersection is non-empty. So in this setting, these things aren't disjoint. So the intersection is not the empty set. Okay. So if we have that, and if we start with, say, a function f sub 1, and this f sub 1 is analytic on d sub 1, okay, then sometimes, not all the time, but sometimes, so there may exist, this is not something that, we'll just assume that this is the case, okay, so then there may exist a function f sub 2 on d sub 2, okay, that is analytic on d sub 2, and such that f sub 1 of z is equal to f sub 2 of z on the intersection. So imagine I have another function that's analytic on this other domain, and it actually agrees with my first function where there is overlap. Okay. If such a function exists, okay, we call this the analytic continuation of the original function. So if if f sub 2 exists, we call it the analytic continuation of f sub 1. Okay, into the domain d sub 2. Now, what does this setup have to do with the theorem that we just proved? Okay, well, by this previous theorem, if such an f sub 2 exists, then it must be unique. So there must be exactly one way of extending that function. Okay. All right. Now, you can get into a more complicated question when, say, you have multiple domains that are overlapping, and if you want to extend, say, so what you're doing here is you have a function that's defined on d sub 1. You're actually wanting to extend it into d sub 2 here. The idea is that extending it into d sub 2, say along, say, well, I drew it as a curve here, but you could do this with line segments. There's a unique way of doing this because if they match up here, by that previous theorem, they're matching up on a subdomain, so they actually have to be equal on the entire domain. And so if such an f sub 2 exists, then its analytic continuation is uniquely determined. Okay. Right, there's basically only one way of doing it. Okay. And so the idea then here is that now we can use this analytic continuation to define a function, f sub z, that is the first function on d sub 1. So the value of this function big F at a point z is little f sub 1 when z not z sub 1 if z is in d sub 1, and it's the value of f sub 2 if z is in d sub 2. And this analytic continuation, of course, works in such a way that it's nice and they agree here on this overlap. Okay. Because of this, this function big F is actually analytic on the union. Okay. So this is analytic on the union d sub 1 union d sub 2. So these two sets taken together. And now you see why it's called analytic continuation or extension of the domain of definition. You began with an analytic function that had domain of definition d sub 1. You found another analytic function that agreed with it on the overlap of some second domain, and then this allows you to actually find an analytic function defined on the union of of these domains. Okay, and so in effect, what you've done is you've taken an analytic function, right? So you've taken an analytic function on some domain, and you have extended its domain of definition in such a way that it is still analytic, and now it's an analytic function that so it's an analytic function that matches the one you started with, where there's overlap, where there's agreement here, but now you've extended it to have new values in a way that it's still analytic and now has a larger domain of definition, including both of those things. Okay. So we say that in this case, right, you can say that big F is the analytic continuation of both f sub 1 and f sub 2 into the domain that's the union of those, d sub 1 union d sub 2. Another way, so common terminology here, is to call f sub 1 and f sub 2 elements of big F. Okay, so f sub 1 and f sub 2 are called elements of this analytic continuation big F. Okay. So this is how this analytic continuation business works. Okay. And so another quick thing that I wanted to mention before moving on to elementary functions, which is just a nice fact about complex functions that satisfy what's called the reflection property. Okay, and so the theorem I'm about to write allows you to predict or know exactly what sorts of functions satisfy this. So suppose f is analytic on D. If I don't specify that D is a domain, it is. Okay, so D is a domain. So if I have function f, it's analytic on some domain D, and we'll say that this domain D, that is a domain that contains a segment of the x-axis. Okay, so it has to contain a segment of the x-axis and whose lower half is the reflection of the upper half along that segment of the axis. Okay, so this is this type of domain that is symmetric with respect to reflection across the x-axis, but it actually contains a segment of the axis itself. So, so that's important here. Okay, and so then, if I look at the complex conjugate of f of z, this is equal to f of the complex conjugate of z. That is, I'm able to move this conjugation operation inside the function for each z in D, if and only if, okay, if and only if f of x is real for each point x on the segment. The segment above being the one that is contained in this D. Okay. All right. So this has an application that we'll see later in a couple chapters ahead. But the main thing I wanted you to note, so I'm also not going to prove this, although it's not too complicated to show. So I will omit the proof. But I will immediately give some examples here illustrating functions that have this property and those that don't. So notice if I have the function z plus 1 and I compute its conjugate, well, actually this is equal to the conjugate of z plus 1, right? And also, if I look at z squared and I take the conjugate of that, that is equal to the conjugate of z squared. Okay? So this works, right, for all z in the plane, right? And so what does this mean in the context of this theorem? Well, note that of course this works, right, by looking at this requirement. I just need to check that x plus 1 is always real. So is x plus 1 is always real, right, when x is some real number on the segment. But what about x squared? Right? That's always real too. And so there's the relationship between these functions satisfying this reflection property and the value of these functions being real on real segments. But you'll note, right, that if you have f of z, which is, say, z plus I, or f of z is equal to, say, I z squared, these do not have the property. So these do not satisfy the conjugate of f of z is equal to f of the conjugate of z. Okay, but you should be able to immediately see that because x plus I is not always real. In fact, it's not real, right? And same thing, I x squared is not real, right? Okay, so this gives a quick way of determining when functions satisfy this property and when they don't. Okay, so definitely in general, do not assume that this is a property that is in general held by functions of a complex variable. Okay. So I don't see any questions about that stuff, so I will continue. All right. So now our idea here is to basically set up a nice bank of complex valued functions. We actually don't have that many yet, right? We've basically talked about we have talked formally about e to the z. Now we're going to talk more specifically about it and talk about its properties. We've talked about polynomials, of course, and we talked a little bit about rational functions, which is a ratio of two polynomials. Okay, but now we want to talk about the functions that reduce to the very familiar kind of basic building block functions that you know from calculus. Okay, so idea, so we want to discuss what are called elementary functions. So what are these? These are functions f of z, where if we just restrict ourselves to, so if we let z be equal to x plus I 0, then f of z is equal to really just f of x. And we want this one to be one of our basic functions, right? One of our basic functions from calculus. So just running through them quickly. The exponential function, log, trig functions, hyperbolic trig functions, and so on. Okay, this is kind of our main things that we want to focus on. Okay, And so, the first one that we want to talk about is the exponential function. So number one is our exponential function f of z is e to the z. Okay, so of course, e to the z, viewing z as x plus iy. This is e to the x times e to the iy, where e to the iy by Euler's formula is cosine y plus I sine y. So you've already done a lot of computations. With this, we consider y to be in radians here, right? And so this is exactly, note, if y is equal to 0, then e to the z is just equal to e to the x, the usual e to the x function from calculus, right? Okay. The textbook makes a note that if we look at the nth root of e, we consider this as e to the 1 over n. But typically, when we're talking about complex numbers, the nth root of e is talking about a set of nth roots, right? So for us in this function, when we write this, this is going to be true. So e to the z is going to be equal to e to the 1 over n, and we're not considering this as a set of nth roots. Whenever the complex number z is, 1 over n for some n, that's, we'll say, in natural numbers. Okay, so when we write this in the context of the exponential function, we're actually not writing it as the set here. I would use set notation if I ever wanted to talk about those things like this. Okay. All right, and of course, we notice immediately, right, that you can deduct or you can deduce the the usual properties of the exponential function. Of course, this is already done for us, not from the fact that this is e to the x and extending this. This is actually, we did this formally, right, thinking of this as power series. Okay, and so you can actually do this, if you like, directly from this, and I think I might have actually worked out that algebra once. So we can also work out, that for instance, e to the z sub 1 over e to the z sub 2 is equal to e to the z sub 1 minus z sub 2. So that can all be justified algebraically using the exact same thing. And so, of course, e to the 0 is 1, and 1 over e to the z in this formula can be shown, this is e to the minus z. Right. Okay. So none of this is very surprising to us. In fact, we've already computed that when we take the derivative of e to the z with respect to z, we get exactly what we expect, which is e to the z. Okay, and this is true for any point z in the complex plane. And so e to the z is entire, not unexpected, right? E to the x in calculus is one of the nicest functions we have access to. Okay. Now, also, e to the z is not equal to 0 for any complex z. Right? This is a fact that, of course, you exploited in various ways in calculus, that e to the x was never 0. Okay. But, of course, there is something a little different right here that we have to say, right? Because what we knew from calculus was that e to the x was actually always positive, right? So while it's still true that e to the z is not 0, it can actually be negative, right? It can actually be negative. So, but one key difference. So e to the z can be negative. We already knew this, right? So, for instance, e to the I pi is equal to -1. Okay. So the exponential function e to the z can be negative, right? So, which is something that wasn't true for e to the x. Okay. All right. Now, if we write, say, e to the z as, say, r e to the I theta, okay, well, then we already know, right, that this r is equal to e to the x, right, and this theta is actually equal to y, right? And so if I wanted to look at the modulus of this functional value e to the z, this is just this r, which is e to the x, and the argument of e to the z is, of course, this y, plus, since writing in polar form, this thing is 2 pi periodic, so multiples of 2 pi here. That's what I get for the general argument, where, you know, n is some integer. Okay. Directly from that, then, is the following. So first of all, the modulus of e to the z is e to the x. So e to the x we know is always positive, so at least the modulus of e to the z is always positive, which of course we expect that to be. But notice something that is also slightly different, is that e to the z is periodic, right? Another difference between e to the z and e to the x, e to the z is periodic. Well, how do I know? Well, e to the z plus 2 pi I is, by the formula that I wrote above, e to the z, e to the 2 pi I. But e to the 2 pi I is 1. So this is e to the z. So e to the z is periodic, and the period of e to the z is 2 pi I, right? So it has period 2 pi I. Okay. All right. So we've already seen that e to the z can be positive and negative, but it can't be 0. In fact, it can be any value you like, right? E to the z can be any complex, or any, I should say, non-zero complex number. All right. So, in order to actually find what z, say, makes e to the z equal to some given complex number, this involves finding the inverse of this function, which, of course, you already know involves a logarithm, so that's going to be the very next function I talk about. Before I do that, though, I thought I'd give one example of this case, and so here, right, so find z such that e to the z is equal to, say, 1 plus I. Right. Well, put both of these into polar form. Right. So e to the z, I could think of that as e to the x, e to the iy. Of course, in polar form, this thing is modulus times e to the r theta, or sorry, e to the I theta. Modulus this is square root of 2, so it's sum of 1 squared plus 1 squared, so it's square root of 2. Okay, e to the, this is the point, 1, 1, that's on the line y equals x, so this is, say, principal argument is pi over 4 here, right? So this is e to the I pi over 4. Okay. Well, then what this means is that e to the x is square root of 2. And of course, y is the argument of this, which, considering this generally, this is pi over 4 plus 2n pi, right, for n, an integer. Okay. Well, we already know what the inverse function of e to the x is for real valued things. And so this implies that x is equal to ln of square root of 2, right? Which we could use log rules to write this as 1/2 ln of 2. Okay. Now, of course, I could factor a pi here and write y as 2n plus 1 over 4 times pi. Okay, thus any z that looks like 1/2 natural log of 2 plus I times 2n plus 1/4 pi, where n is just some integer, works. So if z is equal to this thing, then e to the z is equal to 1 plus I. Okay, so if z is of that form, then e to the z is 1 plus I. Okay, so this gives us a method here for finding such such a complex number. Now, we're actually going to use more or less this method generally to be able to talk about the complex valued function log z. Okay. Okay. So let's continue this. So we want to use this last example to help define the function log z, which is my inverse function to e to the z, just like ln of x, the natural log of x, was defined to be the inverse of e to the x. Okay. So how does this go? The idea is I want to solve the equation e to the w is equal to z for w. Okay. And here, the z is any non-zero complex number. Okay. So from that, what I said just a second ago, this equation always has a solution so long as z is non-zero. Okay. And so let us do the usual thing here. Let's write z in polar form. So we'll write z as r e to the I theta. And let's actually go ahead and use the principal argument here. So I'm going to write that as, capital theta. You don't have to worry about distinguishing that too much because I'm going to express here that this capital theta is between minus pi and pi. So this is the principal argument that I'm using here. And let w be equal to u plus iv. Then rewriting this equation that I'm trying to solve in terms of this, just like we did in the previous example, is e to the u, e to the iv is equal to r e to the I big theta. Okay. Which immediately tells us, similar to how it did in the last example, that this little r is equal to e to the u. Right? And this v, if you like, is that is this thing. It is immediately determined by this capital theta plus 2n pi, right? Just like in the previous example. Okay, where again n is just any integer. Okay. Well, this r is a real number, u is a real number, and so this piece is equivalent to the usual defining property of the natural log, which is that natural log of r is equal to u. So this is u is equal to ln of r. These two things are equivalent here. Okay, and thus this equation that we call star, so star is satisfied if and only if w is equal to what? Well, just like we saw in the previous specific example, w needs to be equal to the natural log, that is the real valued function, ln of r, plus I times this capital theta plus 2n pi. Okay, where n is an integer. All right, so we did solve that equation as we like. Thus, if we define log z to be exactly this value, so ln of r plus I times big theta plus 2n pi, where n is an integer. Okay. So if this is what we mean by log z, then e to the log z is equal to z, right? Where z is non-zero. And that's exactly what we want. Okay, now I'm going to write a little tombstone here because this is kind of a proof statement. Okay, we're rather just coming up with a motivation for actually defining log z in this way, and we did it in such a way that we solved this original equation we wanted to. So we have found this suitable inverse thing. Now the reason I want to be careful here and not just call this an inverse is that you'll notice log z by definition is multi-valued. All right, so this is multi-valued. Okay. So this is very important to keep track of. If we want to work with a part of this, right, a part of this log function where we have made it into a single-valued, honest-to-God function in the normal sense, we have to do something called taking a branch. Okay, and so I'm going to talk about that in just a second. But this is the definition, okay, of the general multi-valued logarithm function of a complex variable. Okay, it just has to be non-zero. Okay, so note we can even do this for, negative numbers. So this log is actually defined for negative numbers. And so, just to rewrite this, if z, which is given in polar form, as r e to the I big theta. So if this is any non-zero complex number, log z is the natural log of r plus I times theta plus 2n pi, where n is some integer. Okay. This is my definition of log z. Okay, so let's do a quick example. So let's let z be minus 1 minus square root of 3i. Okay. Then immediately writing it in polar form, r is equal to, so this is square root of minus 1 squared plus minus root 3 squared. So this is square root of 4, or 2. So r is equal to 2. And theta is equal to, big theta is equal to, let's think, minus 1 minus root 3. So this is in the third quadrant. So the principal value here that I'm going to take is minus 2 pi over 3. Okay, thus log z is natural log of 2 plus I times minus 2 pi over 3 plus 2 in pi, and n is an integer. Okay. All right. So then if I take something of an expression of this form and I exponentiate it e to that, what do I get? I get minus 1 minus root 3i. Okay. All right. And so note that there's some things that we have to be careful with here, right? So e to the log z is equal to z. That's fine. Okay, that is fine. This is actually how we defined log z. But log of e to the z, this is more mysterious, right? This is more mysterious. The reason this is more mysterious is because this is not a full inverse in that sense. There's some issue here that occurs. So what do I mean? How can I see this? Well, one thing to note is that log z is actually the natural log of the modulus of z plus I times the argument of z. So here's a key way of thinking about this quickly. Right, that's exactly what you're doing here. Right, r is exactly the modulus, and this is exactly the argument. You just took principal argument plus 2 in pi, but that is literally another way of writing the argument. Okay. All right. And of course, we know that the modulus of e to the z is e to the x, and the argument of z is just y plus 2 n pi. Right? We took y to be that principal value, or rather, we took the principal value to be y. Okay. And so, if I were to look at log of e to the z using this, then what do I get here? I get the natural log of the absolute value, or rather the modulus of e to the z, okay, plus I times the argument of e to the z. It's just directly from rewriting log z in terms of this. Okay. But this is ln of e to the x, right, plus I times the argument of e to the z is actually just y. The argument, sorry, I put argument of z here. This is argument e to the z. So the argument of e to the z is just y plus 2n pi. Okay. But ln of e to the x is just x. So this is x plus iy plus 2n pi. But then this is just x plus iy plus 2n pi I, right? But x plus iy is z. So this is z plus 2n pi I, where n is some integer. Aha! And so, log of e to the z is z plus this 2n pi I. It's multi-valued, right, in general. Okay. And so this is what we get here instead. So we don't have a full inverse in that sense, which of course you should have expected because of this thing being multi-valued by definition. Okay. But of course, you're right to actually want this to be smooth and slick, and you want log of e to the z to be equal to z ideally. So how do you deal with that? The idea is to look at the principal value of the log, which you can, of course, think of as being obtained when you take the principal value of the argument or you take n equal to 0. Okay, and so to remedy some of these nasty things, I want to talk about the principal value of log z. And so the principal value, okay, which we're going to see, we're going to eventually call this the principal branch of this log function. So the principal value of log z is the value obtained when n is equal to 0. Okay. And we call this log z. Okay, with a capital L. So capital log z then is equal to the natural log of r plus I times the principal argument theta here. Okay. Note, this is single valued. This is not a multi-valued function. This is single valued. Okay. And in general, it's actually really easy to rewrite this in terms of the general log z. In general, log z is equal to the principal log of z plus 2n pi I. Okay, where n is some integer. Okay. When this z is actually a real number, this just reduces to the usual natural log. Okay. And so in that case, this natural log is actually equal, this log z is actually equal to the natural log. Okay. All right. So let's now compute with this principal log a little bit. So first of all, what is log of 1? Well, this is natural log of 1 plus I times 0 plus 2n pi. So this is actually equal to 2n pi I. Okay. What is principal value of log of 1? It's 0. Okay. Which is exactly what we expect. Okay. Now, the nice thing about this, of course, is that just like the exponential function was allowed to be negative, well, naturally, this means that we are going to be allowed to actually find the log of negative values. Not 0 values, but negative values. Right? So for instance, what about minus 1? Right? So what is log minus 1? Well, this is natural log of 1 plus I times pi plus 2n pi. So this is 2n plus 1 times pi I. Okay. But now you see that this has a different principal value here in the argument. And so the principal log of minus 1 is pi I. Okay. All right. So that's that. Yekta, yeah. So this general log z and principal value of log are related. Well, yeah. I mean, I wrote it. I actually had it on the same sheet. So this is how they are related, right? So this capital L log is the principal value of the log, and it is all it is it's the value of the log where n is equal to 0. So you take n equal to 0 here, so you're getting this principal value. So rephrased in another way, it is the value of this log where the only angle value you take here, the only argument you take is the principal argument. Okay. And so yes, it's different because when you're using lowercase l, that log z function is multi-valued typically, right? And you see that this has multiple values. So selecting the value when n is equal to 0, that is me picking out that principal value that I'm calling capital L log z, okay, or the principal value of the log. Okay. All right. And so this is going to lead naturally into a discussion of something that's very important, which involves the notion of branches. Okay, and so branches and derivatives of log. Okay, and so just to remind us, if we have z that's already in polar form, so we'll say this is z is r e to the I theta, and if we think of theta as being, principal value of theta plus 2 n pi here, then this is the general form here, right? So this theta is the principal argument of z. Then log z is natural log of r plus I times that principal value, big theta, plus 2 n pi. Rewriting this using little theta just to save space, this is ln of r plus I little theta, right? This is multi-valued, just like we saw before. Okay. The idea is to restrict the value of theta in some way. So restrict the value of theta. So how do I do this? So let alpha just be some real number. And so the idea is to let theta be restricted by this alpha. Let it be between alpha and alpha plus 2 pi. Okay. So we consider this instead. And so suddenly, if I look at the log here, so log z is natural log of r plus I times theta, where r is some positive real number, and alpha satisfies the following, so theta is strictly between alpha and alpha plus 2 pi. So this is what I want to look at. Okay. Well, then this has components. So u, say, of r theta here is actually just equal to natural log of r. And v of r theta here is just equal to theta. So this is actually single valued and nice, right? Because this, whatever alpha I fixed here, because I'm going from alpha to alpha plus 2 pi, right? And this theta is 2 pi periodic, right? So it's when I get to 2 pi that I've come full circle here. And so this, however I've done this, this is single valued. Okay, this is single valued. Okay, it's actually also continuous in this domain. Okay, and so it's also continuous. Now, about continuity, it would be a little trickier if we actually didn't have strict inequalities here. Okay, but because we are not including this angular value alpha, it's continuous everywhere on this specified domain. Okay, and so actually, not only that, it's better than continuous. It is actually analytic. Okay, and the reason that it's analytic is I can show, right? So also note, even better, this is analytic. How do I know that? So this satisfies the polar Cauchy-Riemann equations on the domain. So it's continuous on the domain, satisfies polar Cauchy-Riemann equations on the domain, so it's differentiable everywhere on the domain, and thus that's it. That's analytic everywhere on the domain. Okay. And so what happens if we actually compute the derivative of this thing? So first of all, might as well show that it satisfies polar Cauchy-Riemann equations. What are polar Cauchy-Riemann equations? Right. So remember, polar Cauchy-Riemann states that R, here I need some paper underneath my paper. So polar Cauchy-Riemann states that R, U sub R, is equal to V sub theta, and that U sub theta is equal to minus R V sub R. Okay. So let's remind ourselves here, our log function has component functions, natural log of R and theta. Okay. And so U sub R is 1 over R. Right? So U sub R is 1 over... Now, I'll just compute all these. Okay, so here. I'll leave this here, and I'll compute them down here. So U sub R is equal to 1 over R, because it's the derivative of natural log of R. U sub theta is equal to 0. V sub R is equal to 0. And V sub theta is equal to 1. Okay. And so, let's check that these satisfy my polar Cauchy-Riemann here. So R times U sub R is equal to R times 1 over R, which is 1, which is definitely equal to V sub theta. Yep, good. U sub theta is 0, which is minus R V sub R. Yep, because V sub R is 0. So satisfies polar Cauchy-Riemann. It's continuous everywhere, so it's analytic on the domain. Okay, and now, what if I want to compute the derivative of log z here? Okay. So what if I want to compute the derivative of log z here, where it's single valued, nice, and analytic, right? It should have a derivative. Well, it satisfies polar Cauchy-Riemann. So according to the theorem, where I stated polar Cauchy-Riemann equations and that condition for a function being analytic, this must be e to the minus I theta. This is a couple videos ago. This must be e to the minus I theta times u sub r plus I v sub r, right? This is the corresponding thing for polar form that we had when we would say that d dz of f of z is u sub x plus I v sub x, right? You could find this just by taking the x partial in both slots. Okay, so what is this? This is e to the minus I theta times u sub r here is 1 over r, plus I times v sub r is 0. Right? And so rewriting this, e to the minus I theta, that's 1 over e to the I theta. So this is 1 over r e to the I theta. But that's z. This is 1 over z. Hey! Right, we kind of expected that. Right, so d dz of log z on this part where it is single valued and analytic is actually 1 over z, which is exactly what we expect. Now, this is true, of course, in general. So this is, so modulus of z is greater than 0, so it's non-zero. And the argument of z is strictly between alpha and alpha plus 2 pi. Now, actually, we can pick a particular alpha here, right? So if we pick alpha to be minus pi, we can do the exact same thing here for the principal log. Thus, right, in particular, we can always do this for the principal log. So this is 1 over z, where again, this is for non-zero z, but also now if we let alpha, all we're doing here is letting alpha be equal to minus pi. Then this is for angular values between minus pi and pi. Okay. So I want you to think here, I'm not going to mention it now, like I said, I may have you thinking about this on your next homework, of why, in order for this to work out nicely, do we have to have strict inequalities here and here. Right. Okay. If you draw the picture and think about what it is that goes on there, the answer is because we have problems with continuity along a ray in the plane if you include one of these ends here. Okay, there's problems with continuity. Okay, and so this is what we did. Now, what we did here in restricting my angular values, right, restricting my argument, what we did is called looking at a branch of a function. Okay, so that is what we did. Okay, so this is the first example. This is kind of one of the most natural examples where this comes up is in the form of talking about logs. But this is something that we are going to talk about for various different types of functions. So this is the notion of a branch. Of a multi-valued function. Okay, so what is that? What is a branch? The definition of branch. So a branch of a multi-valued function is any single-valued function, big F, we'll call this multi-valued function little f, is any single-valued function, big F, okay, that is analytic in some domain, so this is analytic in some domain at each point z of which the value f of z is one of the values of f. Sorry, of little f. If you're just listening to this, that might sound a little confusing. So canonical example is what we just did, right, with the log. That was the notion of a branch of a function where we took the branch of the multi-valued log function, log z, and just looked at a particular slice that we needed to that allowed us to say, oh, well, actually, this is single valued on this piece, and it's actually continuous and actually analytic, right, on that whole piece. And so this is the notion of a branch. So we see now that the principal, taking the principal value, capital L log z, was an example of taking a particular branch. So in fact, we're going to call that the principal branch of the logarithm. Okay. Okay, so we're going to start here tomorrow and talk more about this stuff conceptually. And we will finish most of this chapter tomorrow, which will put us on pace to maybe start talking about integrals by the end of the week. So that's the idea. If not, then it'll be first thing next week. Okay, after the midterm. So you're gonna have another homework this week, and then you're gonna have a midterm at the end that's going to be due at the beginning of next week, and then we'll continue from there. So that's the idea. So the material that we're about to get to next week is really like probably the most important part of the course, where we're going to get to something called the Cauchy integral formula, which is, if you tell someone that you took a complex course, then the most reasonable thing that they would assume from all of that, right, of all the things you may have seen in your complex course, they're going to assume that you've seen the Cauchy integral formula, because it is like the thing. It is the thing that we're headed towards, and applications of the Cauchy integral formula is kind of the rest of the course after that. So what we're about to do is kind of the entire point of this course, all right? And that's the reason for all this background stuff that we have to do. Okay, so anyway, that's that. So I will see you all tomorrow.